In distributed systems, every field definition functions as a critical architectural boundary. When schemas lack boundaries, engineers append fields to accommodate every new feature request. The schema accumulates uncontrolled weight until the data model shatters under its pressure, fracturing the downstream microservices that depend on it. Platformized design solves this by splitting the problem. We build entities with a stable, immutable core, while simultaneously allowing safe extensibility on the periphery. Without this separation, you see the classic symptoms of poor modeling: rapid schema drift, massive data duplication across databases, and API updates breaking client integrations. To see how to prevent this, we are going to build a production-ready, fully qualified domain name entity, an FQDN, from scratch. We start from a blank slate. Selecting the correct field types when an entity is first defined prevents the service from degrading into a tightly coupled monolith. The first structural column we drop in is the lifecycle backbone. Every entity requires an ID, creation date, and updated date for basic traceability. We also include a dedicated revision slot. This acts as a mechanism for concurrency control. In a distributed environment where multiple services update the same entity asynchronously, the revision field rejects out-of-order updates before they can corrupt the database. Next, we map the entity's relationship to people. Engineers must never assume reference equality between a human user and a system identity, even if their data values match today. Human identity evolves independently of system platform logic. A single person might interact as a contact, a registered member, or a temporary visitor. Each of these requires a distinct structural representation. Collapsing these into a generic user field causes identity mismatch. That leads to permission bleed, where users gain unauthorized access, and it triggers cascading integration failures across third-party tools. These standard lifecycle and identity fields form the immovable anchor of the entity. They guarantee conflict resolution and auditability, regardless of how large the underlying dataset eventually grows. With the backbone secure, we attach core attributes using standard prototypes, like strings, booleans, and integers. However, raw primitives introduce serialization ambiguity. The system cannot distinguish a missing variable from one intentionally set to 0. If the system assumes a missing field is just a default 0, it will write that 0 to the database, actively overwriting valid data. To resolve this ambiguity, we require wrapper types. By encapsulating our primitives in explicit wrappers, we establish clear null-like semantics. The system can now preserve a missing value without defaulting. For fields requiring a fixed set of allowed values, like statuses or categories, we use enums. These enforce compile time correctness, but they must be restricted to small, highly stable value sets. Every enum definition must include an unspecified 0 value as the first option. Without an unspecified default, a client reading an unrecognized new enum value will incorrectly default to the first defined item on the list. That produces an invalid state and breaks backward compatibility the moment your schema evolves. By wrapping primitives to prevent null collisions and strictly defining enums with safe defaults, we protect the core schema against data drift and ambiguous mutation requests.
Next, we add repeated fields to model bounded collections that belong entirely to the entity, like an internal list of specific tags or attributes. But we must enforce a strict boundary here. If a list can grow unbounded, or if the items inside it require their own independent life cycles, they demand their own distinct API endpoints rather than a repeated field. We carefully establish clear protocols for regulated data. Sensitive fields holding PII or payment information must carry strict explicit annotations. This ensures the platform automatically encrypts them at rest and completely filters them out of all system logging paths. Similarly, if the entity contains user-facing text, particularly inside repeated objects, those fields must be explicitly marked as translatable to enable downstream localization. In a standard update, unmentioned fields are replaced with nulls, wiping out existing data. We prevent this by mandating field masks. The payload passes through the mask, allowing only explicitly validated fields to securely patch specific blocks. This guarantees true patch semantics. It clearly isolates updates to specific nodes, significantly improving the safety of concurrent API calls. Bounded collections, encryption annotations, and field masks act as the armor for the core schema. They ensure high-volume mutations remain secure and predictable. Up to this point, we have built a tightly constrained core, but this introduces an architectural tension. How do downstream applications add their own custom product-specific data without violating that core? Firm. Optional application logic and user-specific metadata belong outside the core entity schema. Instead, we utilize data extensions. These allow clients to attach structured custom fields to the entity, partitioned into isolated vendor-specific namespaces outside the core structure. This distinct namespace model enables marketplace flexibility. A partner application can iterate on its own proprietary data requirements while the core schema remains stable for everyone else. Within these extensions, you often need flexible inputs. When modeling generic fields, you prioritize a one-of field over a struct. A one-of forces a predictable, type-safe choice between predefined schemas. A struct allows arbitrary JSON payloads. It sacrifices type safety and should only be deployed when the incoming data structure is genuinely unknown. Finally, for basic grouping and filtering, we provide tags. Tags offer lightweight, user-driven classification. They are not intended for storing structured, business-critical data. Offloading optional data to namespaced extensions and tags perfectly enables extensive product customization without triggering any downstream schema bloat. This is the fully realized FQDN entity. Notice the distinct visual boundaries. We have a universal core at the center, masked boundaries protecting the inputs, and a modular extensibility layer on the outside. The universal core remains aggressively minimal. It houses only identity references, lifecycle metadata, and the required shared domain primitives safely wrapped to preserve structural intent. The extensibility layer absorbs all product variation and marketplace complexity through strict namespaces. Dynamic data payloads plug in and out without disturbing the locked center. A properly modeled entity anticipates evolution. It handles the unknown by strictly defining exactly where that unknown data is allowed to live. Platform scale is a product of structural intent, rather than a result of accommodating every individual data request.